This is a tutorial video about generating adjustable pulses from Arduino using interrupts. It could also be done in the main loop without interrupts, but it will get unreliable and jittery if your code also needs to do other stuff besides generating pulses, especially if you need the pulses to go below 1 millisecond range. As you can see, it is currently generating one pulse after every 100 microseconds. A little backstory. About a year ago, I helped someone who has bought an old Soviet-era milling machine that had its control box missing. The brains of the device have either been stolen or sold separately before he bought it. The X, Y and Z axles of the machine were controlled by a stepper motor, and we needed to generate pulses up to 5000 pulses per second to drive it, which means a pulse after every 200 microseconds. Since the machinery is heavy, we also couldn't just start at 5000 pulses per second. We needed to accelerate and decelerate to alleviate the forces caused by inertia. For this tutorial, I have connected a potentiometer to analog pin 0, so I can adjust the pulse frequency, and I have connected my oscilloscope to pin 8 to read the pulses. Since timer 0 is used by the millis library, I'm going to use timer 1. It is probably not necessary, but just to be on the safe side, I'm going to disable interrupts while I'm doing the timer setup. I am enabling compare mode for timer 1. This means that the timer will be triggered when the timer counter reaches the compare register value. Also, I am enabling prescaler 64 for the timer. This means that it takes 64 CPU cycles to count the timer up by 1. Arduino is 16 MHz. 1 second divided by 16 million is 0.0625 microseconds. This means that with prescaler 64, one timer tick is 4 microseconds. And if I want 100 microsecond pulses, I need to set the compare register to 25. And -1 since the counter starts from 0. And the last setup line turns on interrupts for timer 1. When timer is triggered, then this is going to be called. Now let's use interrupt to generate pulses from pin 8. I am going to use direct port manipulation to make it faster. And add a little delay to the pulse to make it more visible. And when we upload it to Arduino, we are seeing one pulse after every 100 microseconds. For the next step, we want the timer to be adjustable, so let's add a variable for period. Since this variable will be accessed from the main loop and in the interrupt service routine, we have to declare it as volatile. This is to prevent the compiler from doing any kind of sneaky optimizations to it. I'm going to update the compare register value in the end of the interrupt service routine. And again -1 since the counter starts from 0. I don't want to change this value outside of the interrupt since I want to make sure that each pulse is finished correctly. Let's read the potentiometer value from analog 0 so we can adjust the pulse length. Since the potentiometer value is not stable, we are going to only use values that have changed more than 5. And let's map the potentiometer value to a new period value. Since integer on the Arduino is 2-byte variable and it can take more than one clock cycle to do the assignment, it can be partially assigned when the interrupt is triggered. We want to disable interrupts while we are updating the variable value that is going to be used inside the interrupt service routine. And as you can see, we can now adjust the gaps between the pulses by turning the potentiometer. Thanks to interrupts, we can do complicated stuff in the main loop, and we don't have to worry about the timing of the pulses. Pulses are automatically generated at the right time by the timer 1 interrupt. To precisely control a stepper motor, it is possible to add step counting. Now it will generate exactly 200 pulses. And as with the period variable, step count can be adjusted in the main program, and the interrupt will take care of actual execution of the pulses. And this is it, and thank you for watching.